Welcome back, lead engineers. Okay, so today we're diving into a brand new explainer, and this one, it is going to seriously challenge you. We're going to use physics to solve a high-stakes, real-world mechanical problem. Basically, we're taking concepts you already know, like work, mechanical energy, and heat transfer, and turning them into an actual critical engineering mission. Our goal? Preventing a catastrophic vehicle failure. Let's take a quick look at the agenda so you know exactly what's coming. First, the runaway truck problem. Second, we'll map out our energy flow physics model. Third, we'll look at constraints and system trade-offs. Fourth, the design challenge rubric. And finally, number 5, a quick recap and a transfer question to wrap things up.
All right, moving right into section 1, the runaway truck problem.
So here's the scenario, and honestly, it's a pretty intense one. Your design problem is to safely halt a massive 10,000 kilogram truck that's heading down a steep hill with a vertical drop of 75 meters. To stop this beast, the brakes have to do work. They need to apply force over a distance to convert the truck's gravitational potential energy into internal energy. If they don't, well, the truck speeds completely out of control, which is obviously what we're trying to avoid. But there is a major catch here. As that internal energy rises, the temperature of the brakes skyrockets. Your absolute constraint for this design, the brake temperature literally cannot exceed the boiling point of water.
Okay, on to section 2, the energy flow physics model.
To actually engineer a solution that works, we have to know exactly where all that energy is going. It's like a giant puzzle. We need a really clear energy flow model to see how the stored energy of the truck's height ultimately becomes dangerous heat. So step 1 is gravitational potential energy. That's calculated by mass times gravity times height. Now, as the truck starts rolling, this shifts into step 2, kinetic energy. That's the energy of motion. To stop the truck, we reach step 3, which is work. The brakes apply friction, bringing us to step 4, thermal energy. Literally, all that mechanical energy is transferred directly into the brake pads as intense heat. Now remember, this entire process is governed by the law of conservation of energy. In a closed system, total energy is constant. It just transforms from one form to another. It doesn't just magically disappear. The mechanical energy at the very top of the hill dictates exactly how much work the brakes must perform. Let's put that into perspective. If the descent generates 7.35 million joules of potential energy, well, your brakes have to absorb 7.35 million joules of heat. That is a massive amount of thermal energy. All right, let's pause for a second. I want to do a quick check to see how manipulating our variables actually impacts this whole system. If you were to redesign this braking system for a truck that is twice as heavy, so let's say 20,000 kilograms instead of 10,000, what do you think happens to the total thermal energy generated in the brakes? Think back to your formulas for potential and kinetic energy for a second. Okay, if you guessed that the heat doubles, you hit the nail on the head. Because mass is directly proportional to both potential and kinetic energy, doubling the mass means the brakes must absorb twice as much heat. If we look at the formulas, PE equals mgh and KE equals 1/2 mv squared, if you multiply that mass, the m, by 2, the energy output entirely doubles. And that pushes your system dangerously close to that boiling point constraint we talked about. Which brings us to section 3, constraints and system trade-offs. Now that we know exactly where the heat comes from, we have to figure out how to manage it. And to do that, we look at specific heat. We represent this with the lowercase letter c. Basically, this is the amount of heat necessary to change the temperature of 1 kilogram of a substance by exactly 1 degree Celsius. It's a completely crucial property because it dictates how much energy your brakes can absorb before they overheat. For example, water has a massive specific heat compared to metals like aluminum, and that is exactly why a pot of water takes so incredibly long to boil on your stove. So let's do our second pause check. Knowing your main goal is to prevent the brakes from exceeding the boiling point of water, which material would make a safer brake pad for our runaway truck? Would it be one with a high specific heat or one with a low specific heat? What do you think? You definitely want a material with a high specific heat. The reasoning here is that a high specific heat means the material demands a lot more thermal energy just to raise its temperature by a single degree. If you were to use a low specific heat material, like lead for instance, its temperature would spike almost instantly under that friction. It would easily shatter our thermal limit and cause total brake failure, and we definitely do not want that. But as engineers, you always have to weigh your design trade-offs, right? One option is to simply add more mass to the brakes. Because heat transfer relies on mass, adding more brake material gives the system a greater overall capacity to absorb heat. But there's a trade-off. It makes the truck heavier. Another option is engine braking. By using the slowing forces of the engine in a low gear, you actually divert work away from the brake pads, drastically reducing their thermal load in the first place. You have to decide what balance is best for your design.
All right, let's jump into Section 4, the Design Challenge Rubric. So, how exactly is your final design going to be evaluated? Your final engineering proposal will be graded using a compact CER rubric that stands for evidence, reasoning, and communication. For evidence, your math must definitively prove that the brake temperature won't exceed boiling. For reasoning, you need to logically defend your material choices and trade-offs using the law of conservation of energy. And finally, for communication, you just need to visually present a perfectly labeled energy flow model. Simple as that.
And finally, Section 5, Recap and Transfer Question. Let's quickly pull all these physics concepts together before you get to work. To recap, your mission requires mapping the energy flow, utilizing high-specific heat materials, and balancing those tricky mechanical trade-offs. You know potential energy transforms into kinetic, and that brake work turns that kinetic energy into serious thermal energy. You also know that selecting the right materials fundamentally changes how that heat is managed. Before you start drafting, I want to leave you with one final transfer question, just to spark your curiosity and test your new skills. Think about this. How would this energy system design and its thermal constraints change if the vehicle was a descending elevator instead of a truck? Seriously, think about where the work is being done, how a counterweight alters that gravitational potential energy, and where all that thermal energy ultimately ends up. It's an interesting puzzle. Good luck with your designs, lead engineers. I know you're going to crush it.